The core idea for this video is that the presence of a nearby double bond makes possible to put a bromine or a chlorine at the allylic position relatively selectively. And this is taking advantage of the fact that if you have a radical with a nearby double bond, that's going to end up being more stable. Much like there's resonance if you had a cation at that position, there's going to be resonance if you have a radical at that position. It's not going to look the same as you might expect because these are single electron processes, so that means you're going to have weirder looking resonance arrows. However, other than the fact that there's 3 resonance arrows instead of potentially 2 or 1 for the system, you're essentially doing the same exact thing. So allylic compounds are going to behave as though they can be attacked from either direction, much as if it were a cation. I've already mentioned in a previous video, the trend for stability of radicals is very similar to cation stability. Tertiary cations are more stable than secondary cations, which are more stable than primary cations, and that's true for radicals as well. Tertiary radicals are more stable than secondary, which are more stable than primary. And in addition, the presence of resonance will shift everything over 1. So just simply recognize that the presence of a nearby double bond increases the stability substantially, as you might expect. This is an electron deficient system, not as deficient as a cation itself, but still, it would like an additional electron, which makes it fairly reactive. You have the capacity to stabilize a nearby radical if you have a double bond present. And what that means is, in the presence of some radical initiator, either AIBN or peroxides, listed here, then it's possible to pop off those positions that are near the double bond, near the benzene ring. So this is an allylic bromination right here. This will be a benzylic chlorination. Same exact idea. Well, we're going to install a BR at that allylic spot. And of course, since we have resonance, it's possible to generate the other product as well, but of course you recognize that these two are in fact the same. However, you do make both of them. Because of resonance, you are generating both bromides at the same time, but of course you recognize that they are in fact the same compound, just rotated 180 degrees. The product of N-chlorosuccinimide reacting is going to provide the chloride at the benzylic position. So in terms of predictive products, this is what you need to know. Add in NBS, which is a source of bromine, a source of bromine plus essentially, or NCS, which is almost exactly the same thing except the chloride there instead of bromine, and it will react in a radical fashion to install the new halogen at the allylic position or at the benzylic position, one or the other. How does it work? Well, for that, I want to talk a little bit about initiators in general and specifically how it applies in these systems. The initiation step for an epoxide is trivially easy. In the presence of either light or heat, either one, what will happen is peroxide will just fragment on its own, and that will generate a pair of RO dots, a pair of oxygen radicals. Those then go on to participate in the mechanism as I'm going to diagram it out for this system. But once that happens, then you get into the chain propagation steps, and again, what you end up doing is converting into the bromide or the chloride, as the case may be. So that one's straightforward. This one's a bit more complicated. The driving force for AIBN initiation is the formation of very stable tertiary radicals, which are stabilized by resonance, but also the formation of nitrogen gas. So when this fragments, what happens is you go and create nitrogen gas, which simply goes away. At the same time, you are creating a tertiary radical that is stabilized by resonance. This is absolutely going to be a one-way ticket, no equilibrium here, not least because as soon as you generate the nitrogen gas, it evaporates off and is lost to the system and goes away entirely. But at the same time, you have simultaneously generated 2 of these tertiary radicals that are stabilized by nearby resonance. And whenever you use an explicit radical initiator, you're actually going to have 2 different initiation steps. There's the one where the material itself, be that AIBN or the peroxide, decomposes on its own in order to provide a radical in general, like this one, but this is not going to participate in the main reaction. You just throw it in to kick off the reaction. And the peroxide is the same thing. It doesn't matter whether we make the AIBN radical as drawn, this is the isobutyl radical, or alternatively, whether you made peroxide radicals, again, you'd make 2 of those, the identity of the radical down here is irrelevant because you only make a tiny amount of it, and then once it abstracts this bromine and creates the real propagating radical, then the reaction is off. So the next step is that this goes and creates a bond to the bromine and generates what will be the propagating radical. Likewise, if you used peroxide as the initiator instead, you're going to do the exact same sort of thing. Either way, key thing that we care about is this radical, which is going to be the propagating radical. I did mention earlier that N-bromosuccinimide, and N-chlorosuccinimide for that matter, are a source of Br+, or maybe even Br dot. In other words, they can serve as their own radical initiator if necessary. AIBN may be a better way of kicking off this reaction, but under the right conditions, NBS can actually fragment on its own to create what will be the propagating radical for this reaction, as well as a Br dot. This will generate both at the same time. So the propagating radical is actually the NBS, the nitrogen-containing part of NBS, and that will then encounter, say, the allylic hydrogen that needs to be abstracted. And so you'll draw this single electron arrow which goes to make a bond with one of the hydrogens at this position, and that will lead to a radical that is allylic, and even though it's primary, again, it's stabilized by resonance. So the key feature of this radical is that it is stabilized by resonance. Meanwhile, what you have done is put a hydrogen on this nitrogen, and now, of course, this radical, allylic radical, comes by and encounters another molecule of NBS. When the allyl radical encounters the bromide, it simply creates a bond to that bromine, making the desired product, regenerating the propagating radical. So now we've regenerated the nitrogen radical. The nitrogen radical, of course, is itself stabilized by resonance in both directions. So this is a really stable radical, which is why this can serve as an initiator in the first place. The nitrogen-bromine bond also is going to be relatively weak, but it's also that the radical is stabilized by resonance. This propagating radical then encounters another allyl, which then removes the hydrogen, which then creates this allylic radical, which is stabilized by resonance, and then this comes and removes the bromine from the NBS, which then creates another propagating radical, and so on. And we plow through the entire rest of the starting material until, coincidentally, radicals start encountering each other. So what happens during the termination steps for this mechanism? Well, it's a massive free-for-all, as any radical that may have been generated in the entire process at any point starts encountering each other. For example, you had a couple of NBSs maybe fragmenting originally, so you've got two Br dots floating around. Could they react with each other? You bet. But you've got a Br dot floating around, and maybe there's some AIBN that was left over from the beginning that once it fragmented to create that single radical, made that instead. Maybe instead what you have is the two remnants from the AIBN encountering each other and making this bizarre looking thing. Maybe instead you have an allyl encountering a remnant from the NBS. Maybe instead you have the two allyls encountering each other. Maybe instead you have the two remnants from the NBS encountering each other. Maybe instead you're making some other products I'm not even thinking of. Radical reactions lead to a giant mess at the very end, but it always happens because of the random radicals that are still floating around, bumping into each other, again, completely at random. They're not attracted to each other in any way. Any radicals that you have generated at any point in the process could just happen to collide with any other radical, and it will make at least a smattering of every possible product. I haven't even diagrammed them all out. I only bothered to draw out the ones that I thought would look kind of weird, not even the ones involving bromine. So obviously, bromine reacting with an allyl makes the product that you want. Bromine reacting with this goes back to NBS. You make everything. However, you don't make very much of any one thing. And again, that's because you only threw in maybe 10% of the AIBN in the first place, and then when you heated up the reaction or blasted it with light to get this reaction cooking, maybe only 1% of it fragmented, and so on. So you don't really have a lot of the radical byproducts, but you are having a lot of potential radical byproducts. And so when you're drawing out one of these mechanisms, the initiation step may involve a couple of steps in order to kick the reaction off. The propagation step is where almost all of the chemistry happens. And then the termination step, if you're drawing out a mechanism, draw like 3 or 4 different random products that could be made via any kind of radical encountering another radical. You make a mess at the end. In fact, this is a reaction that just doesn't involve all that much control. Bear in mind that you are dealing with resonance here, which means you're attacking both sides. And in this case, that leads to the exact same compound, but it doesn't have to. What if instead we'd had, say, a carbon at that position? Would you make this product? You bet. But you'd also make something else, including both enantiomers. So just pay attention to the fact that radical reactions are going to lead to a mixture of products. Not to mention the fact that even though I didn't draw it out, there are 3 hydrogens there which could lead to different products potentially, and you should at least think about which ones are made. And you should maybe even think about the fact that we're drawing this at the moment as a cis double bond, but it's not out of the question, especially when you're dealing with radicals, that it could isomerize and maybe you have the trans double bond. Anyway, radical reactions are often unselective, and when you're dealing with resonance, things could get complicated as well.